Welcome to this new video. In this video, we're going to learn about a new probability distribution. In this case, it's going to be the Log Pearson type 3 distribution. So far, we have covered four distributions. Three so far. We're going to cover the fourth now. The three that we have already covered will be the Gumbel and binomial probability distribution plus the normal probability distribution. So we have those. We already covered those three in the previous videos. Now we're going to learn about the Log Pearson. And we're going to compare again to the Gumbel just to see how different distributions can still give us. Since they are different, they can give us different values as results. So to do that, we're just going to solve this problem here. Um, we're just going to do this problem for this section. So in this problem, we're going to be analyzing floods on the Clearwater River. Obviously, this is an example that you can apply to any river to have data from. So let's start. We are giving a long record, 55 years of streamflow data for the Clearwater River at Kamiah, Idaho. This data helps us understand the typical flow rates of the river and predict the size of floods that might happen in the future. We can use different statistical methods to analyze flood data. Two common methods are Gumbel, or also called extreme value type 1 distribution. This method works well for floods with short durations and is generally used for peak annual flows. Um, Log Pearson type 3 distribution is the second method that we're going to use. This method is suitable for a wider range of flood durations and can handle some skewness in the data. We're already given some data and some values. What we did with the 55-year data that I have it here, so from 1911 all the way down to 1965, all these two columns are the 55-year data set that we have for this river. We calculated some statistical parameters from the 55-year streamflow data. We used both the Gumbel and Log Pearson distributions to estimate the size of floods that might happen every 10 years and every 100 years on the Clearwater River. So this part is shown here. The way we found these values, these four values, is the same way we're going to use to find the next part of the problem. So what we need to do, we are going to look at a shorter period. We're interested in how flood predictions might change if we only consider data from a shorter time frame. So we'll focus on the middle 25 years of the 55-year record from 1927 to 1951. So it will be only this section here. And I already have it. Let me hide this. Hide columns. I already have it here. These years that we're going to be interested for the second part of the problem. Um, we need to calculate the average flow rate and how much the flow rates vary around the average or standard deviation. Since we are using the Log Pearson distribution this time, we'll also calculate these statistics, the average and standard deviation, for the logarithms of the flow rates. Additionally, calculate the skewness, which tells us if the data is symmetrical or leans towards higher or lower flow rates. Use the Gumbel and Log Pearson distributions with the data from the 25-year period. Estimate the 10-year flood and the 100-year flood for these shorter timeframes. These are the return periods that we're going to be interested in. Finally, we need to compare the flood predictions from the 55-year data with the predictions from the 25-year data for both the Gumbel and Log Pearson distributions. By analyzing these comparisons, draw conclusions about how the length of the data record can influence our predictions of flood sizes on the Clearwater River. So we'll need to use some tables. It will be in our case table 13.5 and 13.4. 13.5 is what we'll need for our Gumbel distribution if we want to find what the flow will be for a given return period. In the previous problem, we solved for the return period given some flows already. We're doing the opposite right now. And to do that, we need to use this table for Gumbel distribution. And we're going to use table 13.4. I know it's very small. We're going to expand it later to solve for Log Pearson type 3 distribution. Same approach, just different table since they are different distributions. So let's start by solving first the values that we'll need to solve for Q10, right? Which represents the flow for a 10-year return period. And we need S bar, we need a standard deviation, and K10 in this case for 10-year return period. And the values of K we can get them from table 13.5. So let's start here. So the value of 10 in our case will be for a return period years of 10, our value of k will be 1.30 or 1.3. And our value of 100 will be for 100 return year periods, 3.14. So we got that, and we need x bar and s. So let's plug that in here. So that's gonna be equal to average of our data, the 25 years. That's what we're given, right? So this is the average discharge in cubic feet per second, as we can see here in the title. And we need to do a standard deviation for the same data. So that's all we need for this Gumbel approach. So we can proceed to solve for those values. So that's gonna be x bar plus our value k10 times our value of standard deviation, and we get 77,000. And for Q100 would be the same approach, x bar plus k100, oh sorry, equal to x bar plus k100 times the standard deviation of our data. So about almost 111,000 if we round up. So this is how we solve for the flow discharge for a 10 return period, 10-year return period, and for a 100-year return period. Now, a similar approach we're going to use for the Log Pearson type 3 distribution. This is what we are going to need to solve first for this distribution. So let's start with the skew of our data. It's 0.67. Now we need to do the log of the mean, but it's not like we should not do the average of this and then calculate the log of the average. We need to find to solve for the log of each single value. So we need to do log of each single one of them, each value. So this will be the log of 68,600. And if we copy the formula, this will be the log values of each single year flow value. And now from that, we need to do the average. So log mean will be average of the log values. So be very careful with that part. And then the standard deviation is gonna be same of the log values. And log skew, the same way we did with the mean and the standard deviation. We need to do the log of the values that we solved for. So if we do, sorry, it should be the skew of these values here. And this is the value that you should be getting. So technically we don't need this here. Okay, so these two values is what we need for the Gumbel. These three values here is what we need for the Log Pearson distribution. Now, how we find the K values for the Log Pearson? So we have 0.1483. So it will be for a 10-year return period, 0.40 will be between 0 and 0.2. So we have to use linear regression. So it will be 0 here, 0.2, and we're interested on this value here for a 10-year return period, and for 100 we're gonna use. So 0.2 for a 10-year will be 1.301, and 0 for skewness of 0 will be 1.282. Now, as we've seen in a previous video, the way to do linear regression with spreadsheets, we use the forecast, and we're interested on a 10-year value. We're looking for 10-year, and in our case, the Y data is where we are missing a value. So it will be this and these two values, because it will be between those two values. Actually, let me format it differently. So So we have this data, and we're interested in this value. What would be the value for this? For a 10-year period, these are the two values, and for a 100-year period, would be 4.2. A 100-year period is 2.472, and for 0, 2.326. And to find forecast of this, our y data will be these two, our x data will be this, and we should get 1.296. Yep, that's correct. Similar way here, forecast 100. No, just that's wrong. We're interested on this value. Our y data will be these values here, and our x data will be these values here. And this is, let me get rid of some decimals here as well. Okay, so this will be our k value. So this is k10, 1.296, and this is equal to this. Now that we don't need the table anymore, let's make it smaller. And now we have all the values to solve. Let's use this equation, 10 to the log of the average x bar plus k10 times the log of s, which is the standard deviation. But we already have those values here. We solve for them. So let's do 10 are equal to 10, and then log of x bar, which will be log of u, is the same average, plus k10 that we solved for, multiplied by log of s. And yep, that's correct. This is the value for q10. And let's go for a similar way. We're gonna solve for q. This should be 100 here. Log x bar, which is u, plus k100 times the log of s, 114. Yeah, that's right. Let me modify this here, 100. Okay, so these are the values using the Gumbel distribution and the Log Pearson distribution, and using only 25 years of data. These are the values given using only 50 years of data. The way we got these values is same approach, except that we rounded up the numbers. But if we compare them, these values are slightly higher than the 50-year data, and we can make an assumption that with less data, these distributions tend to over predict. We tend to get higher numbers. So I think that's a pretty good conclusion that we can make on this problem. I hope this was clear for you guys to understand how to solve for a specific float in a return period of interest using the tables. And yeah, good luck solving these problems.